My guiding question was, in long jump, what are the differences of motion of pushing off with your left foot compared to your right? The goal of this research is to establish the advantage of using the subject's right foot or left foot to jump off with, and to explain what motions give him this advantage. My hypothesis is that if the subject pushes off with his left foot, he will get farther. I can make this claim on the idea that when the subject pushes off with his left foot, he will drive his dominant hand forward and this will propel him. In this study, Nicholas P. Linthorne looked at the biomechanical principles behind the successful execution of the run-up, takeoff, flight, and landing phase in long jump. He showed that in order to get the best jump distance, the athlete needed a large horizontal and a large vertical velocity. This is important for us to know in order to compare the effects of using right foot or left foot on the subject. The other important research that Linthorne showed was that during the takeoff, the athlete experiences a ground reaction force that tends to change the forces acting on the jumper. One change comes from the braking impulse being greater than the propulsive impulse. This causes the athlete's forward horizontal velocity to be reduced during the takeoff. He also explains that when you push down to jump, the ground pushes back, and this gives you your vertical velocity. Going back to our hypothesis, we predicted that jumping from the subject's left foot would be more favorable because it would allow the subject to drive his dominant hand up and increase the vertical velocity. In this next study, researchers looked at how the mass and force put on the arm affected the long jump performance. In their study, they used a Paralympic upper limb amputee and added mass to his arm. The more mass they added, the better performance the subject had. They concluded from their research that increasing prosthetic mass could be an interesting strategy to improve long jump performance. Thus, we can assume in our study that pushing off the left foot and driving with the dominant arm will give the subject a better performance because they will have more muscle in that arm and thus more mass and force. In this study, Dr. Paul Bryce used quantic biomechanics to calculate vertical and horizontal velocity during triple jump. Although triple jump and long jump are not the same, their takeoff are nearly identical. From the recorded data, Bryce concluded that during takeoff, the flexion of the athlete's knee, hip, and ankle all increased, allowing the athlete to quickly extend off the board and increase his vertical velocity. This data is important to us because it shows the importance of which leg the subject pushes off of, because this push-off really gives the subject the full vertical velocity. Our subject was a 16-year-old male with years of experience in track and field. He had a height of 1.6 meters and a weight of 631.65 newtons. He is also left-handed. Our footage was captured with a standard MacBook Air camera with a recording speed of 30 frames per second. Both videos were captured in the same place. For both trials, the subject was placed 18.396 meters away from the pit. Using a standard speed gun, we tracked the subject at roughly 6 meters per second for both trials. In the data analysis, the subject was tracked from their waistline. The subject was placed 18.396 meters away from the pit and then instructed to run and jump and perform his long jump. Here are the two trials we collected, clocking them at roughly about the same speed. graph, we can see the distance covered by the subject vertically and horizontally in the left foot jump. Let's start by looking at the horizontal distance. We originally measured the jump at 2.5 meters. This is very similar to what the graph is showing us because looking at it, we can see that the dots right here decline, meaning the subject is moving away from the platform, which we see from the point of origin up that he is. This jump traveled farther than the right foot push-off, which traveled 2.3 meters. The next points on the graph are the blue points. If we look at where the points are, we can see how the vertical velocity of the subject goes up and then carries, or continues, and then begins to decline. If you can see the decline here, it's very minor, but it is declining. That is basically the decrease in the vertical distance. Looking at this graph, we can see the distance covered by the subject vertically and horizontally in the right foot push-off. Let's start with the horizontal distance. The horizontal distance is very similar to the left foot push-off. If we see here, we have a decline, meaning the subject is moving away from the point of origin, which he is. And then if we look, the only major difference there is that in the right foot push-off, the subject traveled 2.53 meters, and the left foot push-off had 2.75 meters covered. Looking at the vertical distance covered, we can see that there's a higher jump to start out with, and then this holds on for a little bit, but not as long as the vertical distance covered in the left foot push-off. We believe this is because the subject is not leading with his dominant hand, not causing such a great distance in the drive forward. In this graph, we see the vertical and horizontal velocity for the left foot push jump. Using the tangent function on Logger Pro, we see that at first the vertical velocity decreases, while the horizontal velocity increases. This makes sense because the peak of the vertical velocity would be at the moment the subject's foot leaves the panel, whereas the horizontal velocity, the push generated by the leg and the arm movement, allow for the subject's horizontal velocity to increase until right at this point, where after that it begins to decrease. In the graph here, we see the horizontal and vertical velocity of the right foot push-off jump. If we look at the graph, we can see that on average there was a greater horizontal and vertical velocity in this jump compared with the left push-off jump. This means that the right foot had a greater velocity than the left foot jump, even though the left foot jump went farther. We believe that this is because although the jump had less velocity, it was able to direct the velocity it had in a straight pattern. It was able to do this because the subject's dominant hand was able to guide it. This is supported by the x velocity in the graph, in both graphs, where we can see that in the left foot jump the points are cleaner. Let me come over to show you. Here's the left foot jump. We can see here on the x velocity that it's in a much more direct and cleaner line than compared to this one. And we see once we get to the top, it gets a little bit more scrambled. This is because the dominant hand is not guiding it, whereas in the left foot jump, the dominant hand is guiding it. In conclusion, we established that the right foot push jump had a greater overall velocity, even though the left foot jump had a greater distance of about 0.25 meters. This is because the dominant hand was able to guide the velocity in the left foot jump, which allowed for a greater distance. Thus, our hypothesis was correct because the left foot push jump is more advantageous because of the support of the dominant hand.